chemical bond and chemical reaction. Think different. 7. Atom structure, chemical bond and chemical reactions are essential knowledges to us. However, there still are some questions need to explain. Why in atoms the electrons won't fall on the nuclei and react with them? Why the electrons are arranged in layers around the nuclei? How do electrons form covalent bonds and connect atoms into molecules? Why some chemical reactions can easily complete, some reactions are very difficult. Is there a rule to follow to speed up the difficult chemical reactions? This video try to explain and give some help to the above questions. 1. Atom and molecule structure. Matter is made up of molecules and atoms. Atoms have nuclei and electrons. Nuclei carry positive charges, electrons carry negative charges, and electrons are arranged in layers outside the nuclei. But why are electrons not attracted by the nuclei and react with the nuclei? Why are electrons arranged in layers and electron orbits outside the nuclei? Why can each electron orbit only accommodate 2 electrons, and the spin directions must be opposite? To answer these questions, because both nuclei and electrons have spins, spins make them magnetic moments. Therefore, in addition to charge interactions, there are also magnetic interactions between them. Charge interactions and magnetic interactions balance each other, making the atomic structure stable. Take the simplest hydrogen atom structure as an example. Hydrogen atoms have a nucleus and an electron, which carry opposite charges, and the charge interaction makes them attract each other. Therefore, their spin directions should be opposite, which makes their magnetic moments in the same direction and repel each other. In this arrangement, the magnetic repulsion and charge attraction between the nucleus and the electron are balanced. The electron moves around the nucleus, always keeping a certain distance. The atom is in a stable state. Atom electrons are arranged in layers. There are 2 electrons outside the helium nucleus. The second electron shares the electron orbit with the first electron. According to the Pauli exclusion principle, the 2 electrons must spin in opposite directions. In this way, the magnetic attraction between them offsets the charge repulsion between them. They keep a certain distance from each other and move around the nucleus. The nearest space outside the nucleus can only accommodate 2 electrons, and the third electron must occupy a space farther away from the nucleus. Therefore, the electrons are arranged in layers outside the nucleus. Electron energy in each layer. The third electron is attracted by the nuclear charge and repelled by the charges of the 2 electrons near the nucleus. The nuclear charge attraction on it is weaker than that to the inner electrons. Then its spin magnetism, to counteract the nuclear attraction, is also weaker. In this way, the inner electrons of the atom spin fast, have strong magnetism, and high energy. The outer electrons of the atom spin slow, have weak magnetism, and low energy. It seems that the farther away from the nucleus, the lower the energy of the outer electrons. Therefore, in chemical reactions, atoms always lose their outermost electrons first. The spin speed of electrons or nuclei in various molecules varies depending on their chemical environments. This is reflected in both NMR and EPR spectra. 2. Chemical bond. Ionic bond. In molecules, the most common chemical bonds are ionic bonds and covalent bonds. When 2 atoms are connected by an ionic bond, one atom loses electrons to become a cation, and the other atom gains extra electron to become an anion. The cation and anion are then attracted to each other by their charges, forming an ionic bond and an ionic compound. In the figure, the sodium atom, upper left, loses 1 electron and becomes a positively charged cation, while the chlorine atom, lower left, gains an extra electron and becomes a negatively charged anion. They form sodium chloride ionic compound through an ionic bond. The ionic bond force is the electric charge attraction. Covalent bond. Covalent bonds contains polar covalent bonds and nonpolar covalent bonds. Polar covalent bond. When a covalent bond connects two different atoms, their electronegativity is different. The atom with a greater electronegativity has a greater attraction for its electrons. Its electrons must spin faster, creating a greater magnetic moment to resist the attraction of the nucleus. The electron pairs in this covalent bond are not located in the middle of the two bonding atoms, but are biased towards the atom with a greater electronegativity. This is a polar covalent bond. Nonpolar covalent bonds. When the covalent bond connects two identical atoms, there is no electronegativity difference between atom A and B. The electron pair is in the middle between the two bonding atoms, form a nonpolar covalent bond. A hydrogen molecule consists of two identical hydrogen atoms. They are connected by a nonpolar covalent bond. In the bond, the spins, green, of the two hydrogen electrons are opposite. Therefore, their magnetic attraction, black, is balanced by their charge repulsion, forming a stable molecule. In each hydrogen atom, the electron spin, green, is opposite to the nuclear spin, pink. Then, in each hydrogen atom, the charge attraction and magnetic repulsion between the nucleus and electron are also balanced. The conclusion: 1. Ionic bonding strength is the attraction of opposite charges. 2. Covalent bonding strength is the magnetic attraction of two electrons with opposite spins. 3. The two nuclei of a covalent bond usually have opposite spins. 3. Chemical reactions. Chemical reactions start with the breaking of the original chemical bonds, and atoms rearrange to form new bonds and new molecules. Since the bonding force of ionic bonds is charge attraction, changing the environmental electric field can weaken ionic bonds. When ionic compounds are surrounded by polar solvent molecules, they are easily pulled apart by the oppositely charged parts of the solvent molecules, thereby dissolving to form solvent-enclosed anions and cations. In water solvents, they form hydrated ions. During the ion bond breaking process, no electron pairs are separated. Ions do not regain original electrons or give up new electrons, but become cations and anions. The figure shows the dissolution process of sodium chloride. The yellow sodium cations are surrounded by the negatively charged red oxygen atoms in the water molecules to become hydrated sodium cations. The green chloride anions are wrapped by the white positively charged hydrogen atoms of the water molecules and become hydrated chloride anions. Generally, soluble ionic compounds can easily break their bonds and form new compounds. The reaction can be completed within a few minutes, and the reaction efficiency is almost 100%. The reactions of covalently bonded compounds are more complicated. To break polar covalent bonds, the reactants can be placed in a strong electric field to move the bonding electron pairs to one side of the atom, turning the covalent bonds into ionic bonds, and then breaking the bonds to generate anions and cations. This is the case when chloric hydrogen gas dissolves in water to become hydrochloric acid. In nonpolar or weakly polar covalent bonds, the electronegativity of the bonding atoms is similar or the same. It is difficult to move the bonding electron pairs to one side to turn the covalent bond into an ionic bond. To break the bond, it has to weaken the magnetic attraction between the electron pairs, and the magnetic attraction in a covalent bond is greater than the charge attraction in an ionic bond. The general method is to reflux the covalent compound solution for a period of time, to increase the kinetic energy of the bonding electrons and eventually break the magnetic attraction between them. Since the energy of each covalent bond is similar, multiple covalent bonds may be broken at the same time, thereby generating multiple reaction byproducts and reducing the reaction efficiency. The magnetic attraction in a covalent bond is caused by the opposite spins of the two bonding electrons. If their spin directions are changed from opposite to the same, the magnetic attraction between them will become a repulsive force, thereby the covalent bond will break. 4. How to change the spin orientation of atoms or electrons. Nuclear spin flip. In an NMR instrument, a sample is placed in a magnetic field. The magnetic moments of all hydrogen nuclei in the sample are aligned or opposite to the direction of the magnetic field. Radio rays are applied perpendicular to the direction of the magnetic field, generating an additional oscillating magnetic field. When the oscillation frequency couples with the hydrogen nuclei spin frequency, the hydrogen nuclei will flip their spins to the direction of the magnetic field. Electron spin flip. In a generator, the stator generates multiple magnetic fields. A rotor wrapped with wires rotates inside the stator. The wire electrons are affected by the variation of the magnetic field. When the variation frequency couples with the wire electron spin frequency, the electrons will flip their spins to align with the magnetic field. Therefore, variation of a magnetic field can make the nuclei or electrons to change their spin's orientation. 5. Methods to promote reactions of nonpolar or weak polar covalent bond compounds. Many organic reactions are to break the carbon-carbon or carbon-hydrogen covalent bonds in reactants. Catalysts are often used to promote these reactions. Most catalyst molecules, except zeolites, contain heavy atoms, that is, atoms have multiple layers of electrons. Structure of heavy atoms in the catalysts. The heavy atoms in the catalysts have 3 to 5 electron layers. The large number of electrons can generate strong electromagnetic fields locally. In addition to using catalysts, some organic reactions are also accelerated in the presence of heavy atoms. 1. The molecules connecting porphyrin rings and benzoquinone can simulate the photosynthesis of chlorophyll. Under the light, spontaneous electron transfer reactions occur within the molecule. In solutions containing heavy atoms, chlorine, bromine, iodine, the reaction rate is faster. This shows that the breaking of covalent bonds can be accelerated in heavy atom environments. 2. Halogenation of alkanes. Under the light, the carbon-hydrogen covalent bonds in the alkane molecules and the chlorine, bromine, and iodine covalent bonds in the halogen molecules break, generating free radicals, which then rearrange to form halides. The halogenation rate is iodine larger than bromine larger than chlorine. Because as the halogen atomic weight increases, the atomic electron layer increases, and the electromagnetic field in the microenvironment is also enhanced. 3. For the film tapes coated with silver chloride, silver bromide, or silver iodide, their photosensitive reaction rates are silver iodide larger than silver bromide larger than silver chloride. Because the heavier the atom is, the more electrons it contains, the stronger electromagnetic field it generates, and the faster the reaction rate. The above reaction shows that when the catalyst, solvent or reactant contains heavy atoms, the reaction can be triggered and the reaction rate is faster. These heavy atoms provide a strong electromagnetic field in the reaction microenvironment. Heating and light radiation are also important conditions. Heating can increase the kinetic energy of electrons, making it easier for them to break covalent bonds. Light radiation continuously disturbs the electromagnetic field in the microenvironment, causing electromagnetic field oscillations and changes, which may cause some covalent bond electrons to resonate, change their spin orientation, break bonds, and trigger reactions. 6. Possible applications. Every year, a large amount of waste plastic and worn-out synthetic fiber clothing are discarded around the world and piled up into garbage mountains. It takes decades to degrade them in nature. Some degraded tiny plastic particles are swallowed by marine organisms and accumulated in their body. After they are captured and eaten by humans, the tiny particles will be transferred and accumulated in the human body. So far, there seems to be no better way to recycle organic matter except burning. Jiang Xiefeng in Shanghai, East China Normal University recently have found a very effective way to break the covalent bonds in organic matter. Using uranyl compound as catalyst to degrade plastics under light. The reaction that takes decades in nature can be completed in just tens of minutes in the laboratory. Uranium atoms have 7 electron layers, which can provide a strong electromagnetic field in the microenvironment. Coupled with the electromagnetic wave oscillations generated by light, the covalent bond electrons in the plastic can easily flip and break the bonds. If this method can be industrialized, it will be a great boon for eliminating pollution on the Earth. Nuclear fusion produces enormous amounts of energy. It can only occur under extremely high temperatures and pressures. For many years, people have been looking for the possibility of nuclear fusion under milder conditions. Nuclear fusion reaction starts with the synthesis of deuterium and tritium nuclei to produce helium. Both deuterium and tritium have 1 proton in their nuclei, and 1 and 2 neutrons, respectively. Nuclear magnetic resonance has discovered that when the protons and the neutrons in an atomic nucleus are not both even numbers, the atomic nucleus has a magnetic moment. Therefore, the atomic nuclei of deuterium and tritium both have magnetic moments. If applying the nuclear magnetic resonance method to the nuclei of deuterium and tritium respectively, let them rotate in opposite magnetic fields, their magnetic moments will be aligned with the directions of their respective magnetic fields and opposite to each other. In this way, when the 2 nuclei meet, nuclear fusion reactions may occur more easily. References. Thanks for watching. Goodbye. October 24, 2024.